Hi students, so welcome to this new chapter Gravitation. Here I am going to discuss the complete chapter Gravitation. Now first we will start with the Kepler's laws. So I am writing down what we will go through in this chapter. So first will be the Kepler's laws. We will start with the introduction and then the Kepler's laws. Then second we will move on to the Newton's law of gravitation. Then we are going to move on to this gravitation law we will apply for the extended bodies. So how to apply this law of gravitation for multiple masses. For multiple masses and continuous masses. And then we are going to move on to the gravitational field. Then next we are going to move on to the gravitational field intensity. So here we will derive multiple formulas, and some of the formulas are kind of particular, so you need to memorize those formulas. And then sixth we are going to move on to the gravitational potential energy. Then one important part is escape velocity, orbital speed, and the geostationary satellite. So these will be the topics. Around 10 topics will be there. Somewhere we can add some extra topics like gravitational acceleration due to Earth is there after this gravitational field intensity, fifth topic. So that as well we will discuss. So now let's move on. Let's start with the Kepler's laws and the introduction to the. So gravitation is much related to our solar system because of the gravitation only the planets are able to rotate in the fixed orbits. So just write down what you know about the Kepler about the gravitation. So like you may be knowing that the sun's position is somewhere in between the solar system, and then all the different planets are rotating about it. So the sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all these planets are rotating about it. So that you know. So before around the 16th century, there was a quite understanding that the complete planets, they rotate about the Earth. So this was called as the geostationary model. It's complete all the planets were taken as they were rotating about the sun. Geocentric model, sorry. Not geostationary, that is geocentric model, where all the planets were rotating about the Earth. But some of the planets were doing kind of a retrograded motion. Like if you observe some of the planets in the sky, if you observe from the Earth, so the motion of these stars were like this, or motion of some of the planets were like this, that were visible from the Earth. So this concept of geocentric model was not able to explain that why that motion is like this, why not something else. And if it would be that all the planets are rotating around the sun, then all the planets must be moving in a path kind of moon. Why they should be performing a motion like this, retrograded motion, as you can see here, like this. So then there were some of the scientists before the Kepler. So they gave the understanding. One of the scientists is Nicholas Copernicus and the Galileo. They gave the understanding that actually all the planets are rotating around the sun. They did collected the data and they were going to establish this using the data. So after the 16th century, there were the scientists, the Galileo and the Nicholas, who were searching out for some other explanation. And they came out with the data. With the data, they came out with the explanation of solar-centric model. In the solar-centric model, the sun was taken as the center of the rotation. Sun was the center of rotation. Then the other planets were rotating about that sun. So this was taken into account. Then using the data of the Nicholas, because Kepler was the student of the Nicholas, he gave the Kepler's laws around the mid of the 16th century, 17th century. He gave this Kepler's laws, where he described how a planet will be moving around the sun, how you can predict the path of that motion. And then around the 18th century, this famous scientist Sir Isaac Newton gave or formulated the Newton's law of gravitation. So it is quite surprising that the Newton formulated these laws of gravitation, which would describe the motion of the planets way after than the Kepler, but the Kepler's laws could explain the Newton's could explain the motion of the planets. So that is how this is the chronology of about what we are going to discuss. First, the Kepler's laws were given, so that's why we will discuss the Kepler's laws, and the Newton's laws could explain the Kepler's laws. So although we will use this formula, F equals to G m1 m2 divided by r square for the proof of the Kepler's laws, but later on we will discuss about it. So somewhere in the Kepler's laws we will use it. Just to memorize this, that the Newton's law of gravitation is F equals to G m1 m2 divided by r square, and later on we will derive it. Okay, now let's start with the Kepler laws. So there are three Kepler laws which describe the motion of the planets. So we are going to start with the Kepler's first law. So according to Kepler's first law, each and every planet is moving in an elliptical path around the sun. So if we take sun somewhere, so then the planet is moving in an elliptical path. So let me explain you something about the ellipse, and then we will understand this law. So ellipse is kind of a X shape, you can say. Now this ellipse will have a center, and center will be the intersection of these vertical line which is connecting the two distant points in this ellipse, and a horizontal line which is connecting a two distant point in the horizontal. Now which one of them is largest, that will be called as the major axis. So this is our major axis in this diagram. The another one which is smaller than that is called as minor axis, and the intersection point of the major axis and the minor axis is called as center. And when we want to form a ellipse, we will take two particular points and then connect a string to these two particular points, and then place a object in that, and then we will rotate it. This is how we form a ellipse. So these two particular points which are fixed, or you can say that the sum of the distance from these two particular points is always a constant, r1 plus r2. Let's say this is r1, this is r2. So then r1 plus r2 is always a constant for a ellipse. So then these two points are called as a focus. So this is first focus, let's call it as f1. This is the second focus, f2. And now semi-major axis is generally denoted by 2a, and the major axis is denoted by 2a, which is the distance between this point and this point, and the minor axis is denoted by 2b, and half of that is called as the semi-minor axis. Half of the minor axis is called as semi-minor axis, and half of the major axis is called as semi-major axis. So half of this value will be b, and b will be semi-minor axis, and this is semi-major axis. So let me write down. A is semi-major axis and B is semi-minor axis. So this is about a ellipse. And now this law says that sun will be at one of the focus. Now it could be any of the focus, and planet will be moving in a elliptical orbit around the sun. So the orbit will be looking like this, and this is how it will the planet will be moving. This is our first law. Now let's move to the second law of Kepler's. So first law is based on the data that Kepler collected. So there is no proof for that. Now for the second law, we are going to prove it using the Newton's law of gravitation. So Kepler's second law, this is also called as law of area. So let's take a planet that is moving around the sun. This is the sun at some point of time at one of the focus, and if we connect this sun to the planet, then the line connecting the sun and planet will be called as the radial vector. So this is, let's say at some point of time the planet is at this position, this is at this position, and at some point of time, so then this will be the radial vector. Let's call it as point A. After some time it will move to the another point B. Let's take it a very small time dt, so the angle will also be covered a small angle, and now this planet is at a new location B. Let's take another point. At another point of time the planet is at this position. Now it could be anywhere, I'm just drawing it to show you. So this is at point C. Now after the dt equal time period it moves another distance. Now distance may not be the same, because we do not know what will be effect of this distance from the sun. So let's take a unequal length. In the dt time it is covering a distance something we don't know, right, but it is moving from the C to D. Now according to the Kepler's second law, the radial vector, this is the radial vector, and the area covered by the radial vector is this area. Let me highlight it. This area, this is the area covered by radial vector in dt time, and this is the another area covered by the radial vector in that much time period. Now according to the Kepler's second law, this area covered will be equal, right? Let me write down the statement of the second law. So according to the second law of this Kepler, radial vector will cover equal area in equal time period, or we can say that for the equal time period the area covered by the radial vector will be equal. The same thing we can say that in this law in different way, that the area covered by a radial vector will be equal in equal period of time. This is how we can say in another way, and if I want to state it mathematically, I can say that the dA by dt is the rate of area covered is constant throughout the time period of the motion of the planet. This is our second law. Now we are going to prove this second law using the Newton's law of gravitation. Now let me just explain you what is the Newton's law of gravitation. So according to Newton's law of gravitation, the force acting between the two masses is g m1 m2 divided by r square, right? So here mass of the sun, mass of the planet divided by r square. This will be the gravitational force. And what will be the direction of the gravitational force? According to the Newton's law of gravitation, it would be the radial direction. So it will be a radial direction. So what is mean by the radial direction? The radial direction means the direction which connects these 2 point masses. Here in this case the planet and the sun will be taken as the point masses, then the radial vector is the radial direction, and that force will be radially inward. This is all, right? Now let's use it. So here this let me draw it again. This was our path of the planet, this was the sun, and the planet was at this location. This was the radial. Now the gravitational force acting on this planet is in this direction, right? Okay, this is in this direction. Now if I calculate the angular momentum of this planet about the sun, what you can say about it? Angular momentum of the planet about the sun. Let's say at this point of time the velocity is v1, then you can say then the angular momentum and the radial distance is r1. L1 is m, mass of the planet, v1 r1, because m r vector cross v vector is the angular momentum. That is the angular momentum. If I ask you what is the torque at that point of time, tau net, you know that on this object only the gravitational force is acting. That's why the torque due to the gravitational force, only the torque will be there due to the gravitational force, right? And this gravitational force is passing through the sun. Because it is passing through the axis of rotation, the torque of this force will be 0. So from here you can say that the tau net is 0. Tau net is 0, then you can say that the torque, that angular momentum will be constant. So L1 is mp v1 r1. That angular momentum will be equal to the angular momentum of C point, And what is the angular momentum of C point? Mass of the planet is not going to change, but the radial distance is changing, that is r2, and the velocity is v2. So this is the angular momentum of the 2 point. Now we are going to use this conservation of the angular momentum for this planet to prove this, that the dA by dt at A at between the A to B is equal to dA by dt between C to D. So because the velocity was v1 and we have taken a small period time dt, so the velocity is not going to change between the AB. So if I calculate for the AB, the area of this arc is, let's say, dA, that will be r1 square d theta, right? Okay. And the length of this arc, let's say L1, can be written down as, or dl1 can be written down as r1 multiplied by d theta, right? Now r1 multiplied by d theta, dl1 can be written down as v1 multiplied by dt, okay, d theta 1. So from here v1 multiplied by dt is equal to r1 multiplied by d theta. So r1 d theta 1 can be written down as v1 dt. Let's place that value here. So dA is r1 multiplied by r1 d theta 1 is v1 dt. So dA by dt is r1 v1. Let's multiply by the mass of planet. So mass of planet multiplied by dA by dt will be equal to mass of planet r1 v1. That is angular momentum. Now if you calculate for the B, C to D, again for the C to D, the dA will be r2 square d theta 2, right? And the again d theta r1 d theta 1 d theta 2 r2 d theta 2 can be written down as v2 dt, right? This length of arc is v2 dt will be equal to r2 d theta 2. Okay, so now dA can be written down as r2 multiplied by r2 d theta 2 is v2 dt. So dA by dt is v2 r2. Let's multiply it by the mass of planet. So then we are getting mp dA by dt is mp r2 v2, which is angular momentum. From this equation and the second equation, this one, I can say that the dA by dt is constant. So this is how I can prove the second law, Kepler's second law, using the Newton's law of gravitation. Now let's move to the Kepler's third law. What is the Kepler's third law? Let's write down this statement. So this is our path of motion of the planet, and the sun is at this place. Then this is the major axis 2a, this is the minor axis 2b of this path of planet, and the time taken to complete one revolution by the planet is called as the time period. Planet is moving and again this planet is coming back to the same position, then the time taken by this planet will be called as the time period. Let's denote by it by the capital T. Now according to the Kepler's third law, square of the time period of the revolution of the planet is proportional to the cube of the semi-major axis. Okay, let me write down this statement. So square of the time of revolution of planet proportional to the cube of semi-major axis. This is the statement. Okay, it was major axis, right? So if I want to write it down mathematically, I can say that t square is proportional to a cube. And again we are going to prove this law using the Newton's law of gravitation. Now Newton's, if you use the Newton's law of gravitation, we need to assume the path of the planet as a circular path, right? So I am assuming that the planet is moving in a circular path. And why is that? Because planet is only affected by the gravitational field of the sun, that we are assuming it. But practically there will be the other planet and there will be the gravitational field due to that. And because of that, there is this path will change. It will not be a circular path, it will become an elliptical path. So elliptical path is a practical path when we take the consideration of the other planets' gravitational field as well. But if I want to do the calculation, I can take only the effect of the sun, and I can do the approximate calculations. So let's consider that the mass of the planet is mp, mass of the sun is ms, the distance between them is r, right? Okay, so we know that because this planet is moving in a circular orbit, so the centrifugal force will be equal to the centripetal force in the frame of the circular motion. So in the frame of circular motion, F centripetal is equal to F centrifugal. Centripetal means a force which is acting toward the center, and that force is a gravitational force. So that force is m g m p, mass of the planet, mass of the sun, divided by distance square, right, according to the Newton's law of gravitation. And the centrifugal force, as we know from the circular motion, would be m v square divided by r. So m, mass of the planet, v square divided by r. So r will be cancelled out, mass of the planet will also be cancelled out. So the velocity of the planet is root g, mass of the sun, divided by, this is the velocity of the planet. Now how do we calculate the time period if the velocity is constant? Time period is total length of path. In this case, to complete a circular orbit, the total length will be 2 pi r divided by the velocity is v. Okay, so t will be equal to 2 pi r, I'm not going to change the r, and divided by v is g ms divided by r. So this will be t equals to 2 pi divided by root g ms multiplied by r to the power, see this is 1 and this is 1 by 2, so that's why that will be 3 by 2. Now let's square both of the sides, then you will get a t square is 4 pi square divided by g ms multiplied by r cube. Now this is just a constant, isn't it? This is just a constant. So this is a constant. Now from here I can say that the t square is proportional to, so this is how I can prove that the planet's time period, square root of the time period, is proportional to the r cube. Now r can be taken as the semi-major axis, right? Okay, now let's do 1 or 2 questions on these Kepler's laws, and then we will move to the next Newton's law of gravitation. So the question is, the time period of the Jupiter is 11.6 Earth years. If the distance of the Earth from the Sun is 1.5 multiplied by 10 to the power 11 meter, then find out the distance of the Jupiter from the Sun. So this is the question. Let's solve it. So we know that t is going to be proportional to the t square is going to be proportional to the r cube. So I can say for the t of Earth square is k times of distance of Earth between the Sun, Earth and the Sun, cube. Similarly for the Jupiter, I can say t of the Jupiter square is k times of distance of the Jupiter from the Sun, cube. Let's divide both of the equations, then k will be cancelled out. So from here the distance of the Jupiter from the Sun is cube is distance of Earth from the Sun cube multiplied by t of the Jupiter divided by t of the Earth square, right? Now let's do the cube root of this equation. So then d between the Jupiter to the Sun is d between Earth to the Sun multiplied by t of the Jupiter divided by t of the Earth to the power 2 by 3. Now we know this value. This value is 1.5 multiplied by 10 to the power 11 multiplied by t of the Jupiter to the t of Earth is 11.6 divided by 1. That is going to be 11.6 to the power 2 by 3. If you do the calculation, then the d of the Jupiter from the Sun will be 7.68 multiplied by 10 to the power 11 meter. So we have completed the Kepler's law of gravitation, Kepler's law of motion of the planets. Now let's move to the Newton's law of gravitation. Again, this law is based on the experiment. So there will be directly the statement of this law. And then we are going to use those statements to form the mathematical formula and then do the calculation from there. So Newton's law of gravitation, the first statement is, let's say there are two masses m1 and m2. The distance between them is r, right? And these are point masses. Then according to the Newton's law of gravitation, the first statement says that the gravitational force, the magnitude of the gravitational force acting between them is proportional to the product of masses. So magnitude of gravitational force acting between the masses is proportional to the product of masses. Second statement is that the gravitational force acting between the masses is inversely proportional to the distance square of the distance between them. The magnitude of gravitational force acting between masses is inversely proportional to the square of distance between masses. So let's denote the gravitational force by F. Then F is proportional to product of masses m1 and m2. Second, the F is proportional to the square. F is inversely proportional to the square of the distance between them. So 1 by r square. If we combine those two statements, we can say that the force is proportional to m1 m2 divided by r square. If we remove this proportional sign, we can replace it with the proportionality constant. Here we are going to denote this proportionality constant by capital G. So then the F is capital G m1 m2 divided by r square. This is the force acting between these 2 point masses. This is just a magnitude. Now let's write it down in vector format. Again, I am going to take these 2 point masses. This is m1, another is m2. Let's find out the force on 1 due to 2. I will denote it by F12. F12 is the force acting on 1 due to, of course this is a force of attraction, so it will be toward the 2. This will be the direction of F12. And next, R12 is the position. R12 vector is position vector of 1 with respect to 2. So when we observe from the 2, this will be the R12 vector. R12 vector direction will be toward the 1 from 2, right? Okay. So first of all, for the magnitude, I can say F12 magnitude is G m1 m2 divided by R12 magnitude, because that is R only. R12 magnitude square. This is the magnitude. And second, we know that the direction of F12, that is F12 cap, is opposite of R12, so that is negative of R12 cap. That is just about the direction. So I can say that F12 vector, which is multiplication of F12 magnitude multiplied by F12 cap, is equal to minus G m1 m2 divided by R12 magnitude square multiplied by R12 cap. This is the F12 in vector format. F12 in vector format, right? Now let's write down the F21. F21 is the force on 2 due to 1. So again, I am going to draw the masses. This is the mass 1. This is the another mass 2. The distance between them is, again, I am calculating the distance of the 2 with respect to 1. That will be R21 vector. So F21 is the force on 2 due to 1. Of course, we are talking about the gravitational force, and R21 vector is position vector 2 with respect to. So I can say F21 vector magnitude again is going to be G m1 m2 divided by R21 magnitude square, because R21 magnitude is equal to R only. And again, the direction of the F21 cap is negative of R21 cap, because F21 is in radially inward direction and R21 is opposite direction. So if you combine, then we can say that F21 vector is equal to negative of G m1 m2 divided by r21 magnitude square multiplied by r21 cap. Interestingly, you can note down one thing from here, that r21 vector and r12 vector are just opposite vectors. So I can say r21 cap is equal to negative of r12 cap. So f21 can be written down as minus of gm1 m2 divided by r12 magnitude square multiplied by negative of r12 cap, and negative will become positive r12 cap, and this is the negative of f12. So f21 vector can be written down as negative of f12 vector. This is an important result. So we have got multiple results from this Newton's law of gravitation. First, we just gave the statement. These were the two statements from the Newton's law of gravitation, and then we formulated a formula for the calculation of the magnitude of the gravitational force, and that force was F equals to G m1 m2 divided by r square. And then next we use the vector format. So F12 vector is minus G m1 m2 divided by r12 square multiplied by r12 cap. We calculated the f21. Now we got f21 vector is negative of f12 vector. Okay, so now let's discuss some of the properties related to the Newton's law of gravitation. So first of all, Newton's law of gravitation can only be applied for the point masses right now. So we cannot apply it for the distributed masses. There we may need to use some other technique to calculation for the calculation. So it's only applicable for 2 point masses. Second, let's say there are multiple masses, point masses only, but there are multiple point masses. So let's say just take 3 masses, m1, m2, m3. Now I want to calculate the gravitational force on the m1. So there will be the gravitational force due to the m2 and due to the m3. So if only m2 was there, then the gravitational force on the m1 was F12 in this direction, and when the only m3 and f1 present, then the gravitational force between them was F13. Now when we bring both of them together, then their individual gravitational force will not be affected. So F12 now as well will be F12 only, although the net gravitational force acting on the m1 has changed when we bring these two masses together. Okay, so one thing we can say from here, that gravitational force between 2 point masses is independent of presence of other masses. Important thing to note down here is, I'm not talking about the net gravitational force. I'm talking about the gravitational force which is acting between the two masses. That will not be affected by the presence of other mass, although the net gravitational force will change, but that I'm not discussing right now, right? Next, the third, if I want to calculate the gravitational force due to the multiple masses on a point mass, then because the individual forces will not change, so that's why F net will be just the sum of F1, F2, F3 in vector format. This is called as law of superposition. So the Newton's law of gravitation will follow the Newton's law of gravitation will follow law of superposition. What is mean by law of superposition? The mean is that if you want to calculate the F net, let's say on the 1 you want to calculate the F net due to the M2, M3, M4, M5, so then that F net will be F1 vector, F12 vector plus F13 vector plus F14 vector, so on. Or you can simply say F net is F1 plus F2 plus F3, so on. So the total sum of the gravitational force is vector sum of all the individual gravitational force. You see, we derived this result. What is this result says? This result says that the Newton's law of gravitation will follow the Newton's third law. What was the Newton's third law? Every action has equal and opposite reaction. So there will be an action-reaction pair. And here we can see that this is a action-reaction pair. So from here I can say that Newton's law of gravitation will follow Newton's third law. So F12 vector is equal to negative of F21 vector. So let's do a small question. So that the mass before question, let's discuss about the universal gravitational constant as well. So what is G? G is called as universal gravitational constant. So universal gravitational constant is a constant whose practical value is 6.674 multiplied by 10 to the power minus 11 Newton meter square per kilogram square. If you calculate the unit, that unit will be Newton meter square per kilogram square. Now this G is not dependent on the medium. I mean, if you take the gravitational force acting on the 2-point masses which are on the surface of Earth, or you take them in the space, that force will not change. It means G is not changing. So G is independent of medium. Second, G is independent of the masses. Third, it is independent. This is independent of distance between them. So it will be always a constant. Next, this is the unit for the universal gravitational constant is Newton meter square per kilogram square. This is the SI unit. Now let's find out the dimension. The dimension of the Newton is mLt minus 2. Meter square is L square divided by m square. So the total dimension is m minus 1 L cube T minus 2. This is the dimension. Okay. This is about the Newton's gravitational constant. Now let's move to the question. So let's say there are 2-point masses m1 and m2. The masses are 20 kg and 20 kg. The distance between them is 20 centimeter. Find out the gravitational force between them. So the gravitational force will be F equals to G m1 m2 divided by r square, right? That is 6.67 multiplied by 10 to the power minus 11. And m1 m2 we need to place in SI units. So SI unit is 20 multiplied by 20. It's the kilogram only. And the centimeter, if we convert it into the meters, this is 0.2 meter, or the 2 multiplied by 10 to the power minus 1 meter. If we do the square, so that is 4 multiplied by 10 to the power minus 2. So 2 cancel out. So F is 6.67 multiplied by 10 to the power minus 11 plus 2 plus 2. So F is 6.67 multiplied by 10 to the power minus 7 Newton. Now see, this value is very small. So that's why we cannot detect this gravitational force between the 2-point masses very easily. We can experience the gravitational force due to the Earth. That is because the mass of the Earth is very large compared to the masses that we practically face. That's why the gravitation, we can experience the gravitational force of the Earth but not of the other masses. So now we will start. After this we will do the law of superposition. How do we calculate the forces using the law of superposition?